Howdy, we're Group 15 and we're going to present the paper Learning to Cache with No Regrets. Here's the table of contents. First, we'll talk about the background and methodology of the paper. Next, we'll talk about the proposed policy, online gradient descent. Then we'll talk about how to extend the results to the cache networks using the bipartite graph, and then the last section we conclude. Let's talk about the background and methodology. Think about why caching matters. Imagine you want to buy a pair of shoes. You go to the shoe store, the shoes you're looking for could be at the store or they could not be available, so you have to wait for the shipping from the remote warehouse. Obviously, waiting for shipping takes much longer time. It is the same for the CPU when requesting files. If you take a look at the figure, it takes 0.5 to 10 nanoseconds to access the cache, whereas it takes 30 to 150 nanoseconds to access the main memory, and the disk storage takes much longer. Naturally, the cache-head ratio becomes an important metric for system performance. The importance of caching could be extended to the cache networks. For example, internet service providers install Google Global Cache within their networks to provide Google content that is frequently accessed by users. If the content is not available in Global Cache, it retrieves the content from the global data center far from the local network. Now let's recall what cache does. Here, imagine a cache that can store 4 chunks of files, and the CPU requests files in a sequence of A, B, C, A, D, B, C, and E. Now after A, B, C, and D, the cache is full, so when E is requested, it needs to evict the file. If the caching policy is least recently used, it will evict file A. If the caching policy is least frequently used, it will evict file D. This shows that policies work differently according to the file request sequences. So, for optimal performance, we need the file request model to determine which policy yields the highest hit ratio. That means we need to know all file request sequences, including future ones, which is impractical in reality. So we try to find a universal caching policy that works well regardless of file request sequences. That is our motivation. We will be using a metric called regret. Regret is a metric to measure how a caching policy performs better compared to the best static policy. If you look at the equation, there's y star and yt sigma. So basically, y star is the cache configuration from the best static policy, and yt sigma is the configuration from the policy sigma. And ft is a function to get the utility of the policy, which is like a benefit we can get from that policy. So having a low regret means our policy's performance is close to the best static policy. Now here is the methodology of the paper. First, we use online linear optimization to match the lower and upper bounds of the policy's regret. From there, we prove that the proposed online gradient ascent policy's regret is at most root CT, where C is the cache size and T is the time horizon. Then we prove that any policy has regret of at least root CT. If we combine these two proofs, we can derive that OGA has the exact regret of root CT, and it proves OGA is an optimal policy. Lastly, we extend the results to the caching networks using a bipartite graph to develop the bipartite subgradient algorithm. Before going further, we will re-examine LRU and LFU using regret. Suppose the initial caching configuration is 1 to C, and the file request sequence goes periodically from 1 to C plus 1. If we think of the utility of a cache hit as W, the total utility is WC, because after C, every request is a miss. For the same sequence, we can think of the best static policy in hindsight, which does not cache C plus 1 in its cache configuration. Then, for every C plus 1 sequence, we get the sum of the utility WC. Thus, the total sum of the utility is WTC divided by C plus 1. So the regret for the LRU policy is at least the difference in the utilities we just got, the worst case and the best static policy. Under the same conditions, LFU yields the same results because the periodic sequences makes the least frequently used file the same as the least recently used file. And obviously, these results are not the best ones, so we will talk about OGA policy.
Online gradient ascent. Let's start by analyzing the regret lower bound. Given that the caching capacity is less than half of the total file capacity, we can prove that the lower regret bound for online gradient ascent is in the order of square root of C times T. If you remember from previous slides, for the LRU and LFU, this bound was in the order of C times T times some, constant. So our lower regret bound for online gradient ascent is a lot lower compared to traditional algorithms. Now let's start to gain some intuition about the algorithm by analyzing and re-examining the simple caching problem. We have a file request sequence here, and we are going to keep a utility vector to keep track of the popularity or utility of the file request we are receiving. So let's receive the first file, and what we're going to do is we're going to increment the first element in this vector, and then we're going to receive the next file, and we're going to increment the third one, and so on and so forth. And this is just essentially a counter vector. And at this point, you might be asking yourself, wait, isn't this just the LFU? We're just keeping track of a frequency vector. And you would be kind of right. The OGA algorithm is actually really similar to the LFU. It can be classified as a normalized version of the LFU. And we're going to circle back to that, but let's move forward for now. The next thing we're going to keep track of is the action vector or the action space. Now, what we want from the action space is for it to help us make decisions about caching. So we wanted to tell us whether we should fully cache a file, partially cache a file, not cache at all. And if we should partially cache, what percentage of the file should we cache? Now, let's examine if we could use our utility vector, which already gives us a lot of information about the utility of the particular file. Can we use that to take actions? And the answer is not directly, because we have some constraints on our action space that prevents us from using a counter like this. And those constraints are, well, we can only store one of each file, we cannot store more. And the other is everything we store must be less than or equal to, the sum of that must be less than or equal to our total caching capacity. I think these are pretty straightforward constraints. Now let's consider a very simple case where we have two files in this initial state, and our caching vector is 0.5, 0.5. What that means is that we store half of one file and half of the other file. Our total caching capacity is 1.5, so we still have some room to cache more. And if you look at the chart, next to the constraints, you can see that it's split into two sections, and it should be really easy to see what these are. So this whole entire Cartesian space is actually your entire vector space for your utility vector. Your utility vector could be in this entire space, but your action space is constrained into this area, which is a subspace of the entire utility space based on this. And it's really easy to see. So if you look at this edge, you can see that if you are storing one file, even though we have 1.5 total capacity, we can only store one of each file. So this would be, you can see that our axes are cut at 1. And this diagonal line, you can see that we can store at max 1.5. So even if we store 0.75 of this, 0.75 of this, we can only store up to here. So the intuition here is that we keep track of this frequency vector, but that frequency vector is outside of our action space. So what can we do? What we can do is actually we can project from this utility space down to this action space to convert our utility vector into something actionable. And the method we're going to use is called Euclidean projection. And the main reason for that is basically because Euclidean projection is convex, which guarantees that there's going to be a unique optimal solution to this. So if we write this problem as a formula, what we are going to do is essentially, and here's another tidbit. So even though here we are keeping a counter with z, we can actually, once we project it down to the action space, we can replace that utility vector with the action vector because it contains the same information, and it's essentially just like a normalized version of that. So we'll replace that z with an older version of y, and what we're going to do is essentially we have the utility vector, we're going to add our gradient, which is just utility gained with the last request, and this is where the online part comes from. So this is a live algorithm, right? As the data comes in, you feed it into the algorithm and it learns. So we are going to feed the utility gain from our last request into our previous action vector, and we're going to project it back onto the space. and that's going to be our next action vector. So now let's see this in action by examining an example. So again, we have the same initial state where we have two files and we store half of them in our action space, and we still have a little more room to go, and we receive a request for the first file. So what we do is we add that utility to our action, our cache vector. Now that utility vector becomes 1.5, 0.5. So we went outside of our action space. So what we do is we project back to the action space, and that would be this ledge, which I think in this simple example, it's really easy to see why that is. And we project to this point here, which is just 1, 0.5. So because this file was requested, its popularity increased. So now we are fully storing this file and only half of the other file. Let's say the next file we requested is the second file, right? So now we go from this point to this point because, again, we go in the axis of the second file. Now we are at 1, 1.5. And this is, again, outside of the action space. So you project it back to the action space. And now we store half of the first file because its relative popularity decreased, and we store the second file fully. And this is just a really simple example to illustrate how the algorithm works in a simplest case. When you have thousands of files, this is going to be a 1,000-dimensional problem, but the basic sort of structure is going to remain the same. So now, obviously, mathematically, this is a constraint optimization problem. So you formulate it as a Lagrangian, and the nice thing that the paper introduces is actually you don't have to check the full optimality condition. You just have to realize that this formulation enforces that your cache vector should be split into three sets. One where it's fully cached, a partially cached, and a not cached version. And another condition is going to be that the fully cached version can only have a single element at most from dual analysis. So that's something that's enforced. And you can find this partition by doing an exhaustive search, but that's an n-squared algorithm, so it's not super efficient. But if you add these additional conditions, one is that the fact that because we are using a convex matrix, our partition is unique, and there can only exist one file that's fully cached. Once we use these, we can use a more efficient search algorithm and get an n log n to solve this. So there is a more efficient way to do the projection, is what I'm saying essentially. Now let's look at some simulations and results. So we start by simulating some of the simpler examples in the paper to check, validate our simulation. This is the fixed step size test, where we take a stationary distribution for our adversary, and we apply the online gradient ascent algorithm. We start by step size 0.01, which is 10 times lower than our optimal step size calculated by dual analysis. And as similar to the paper, it doesn't converge to an optimal point because it's just too low. Next, we can check 0.1, which is, again, by dual analysis, is the optimal step size for our parameters. And similar to the paper, it converges to the highest peak, the highest average hits. And then we can check a case where it's too large, such as step size equal 2. And similar to the paper, it converges initially faster than the optimal step size, but it converges to a lower peak. And this just validates that our simulation is, valid. Let's check another result from the paper where we use our algorithm on a synthetic website traffic. To generate the synthetic traffic, we use ZipF distribution, which, according to a paper that our paper references, that most web traffic on CDNs follow. The paper doesn't detail what exact parameters they used for this distribution, so we picked our own. But the PMF looks like this, and the basic intuition is that a small minority of files are vastly more popular than rest of the files. And as expected, our simulation performs very similar to the one in the paper where the LRU is the worst in this test, and our OGA performs very similar or at the same level as the LFU, and best static also performs at a similar level. So the results are very similar. Now, we did make another graph that we think is interesting, and in this graph we compare the caching decision vector over time. So let me explain the axes here. The vertical axis is the time starting from the top, so that's the first request, and at the bottom is the last request. And the x-axis is your files, and the brighter a spot is, that means that the file is more cached or less cached. And for LRU, since it makes decisions in chunks, it's going to be bright or dark. And the first thing you should notice is how spotty or noisy LRU is, because it makes decisions based on time locality, and it makes decisions per chunk. So it like either evicts a chunk or admits a chunk, whereas the OGA makes smoother decisions and gradually changes its distribution. Um, an even more interesting rethink result is the following, which circles back to a thing we mentioned earlier. If you compare the distribution to the LFU, you'll see that it's, as predicted, is very similar to the OGA. OGA is a normalized and a smoother version of the LFU, but it pretty much has the same structure. And this again circles back to the same point that OGA is just a normalized version of the LFU. Um, and all the simulation code is available on our GitHub. Feel free to check it out.
Then I am going to talk about how the authors use their method on the bipartite graph. And the bipartite graph is a type of the graph with two sets of the nodes. And the nodes, they are not connected with each other in the same set. And such as for the figure on the right, we have the set 1 as a student, and we have set 2 as a groups. And for our case, we have the users and caches. So here we are talking about the symbols of the nodes and the edges in the graph. And suppose we have the group of the users in the letter A, and we have also a group of the caches in the letter J. And we are showing the edges between the nodes with the letter L, and the LIG, it means if the LIG is 1, then that means that user I is able to access G. So the goal of the method is to maximize the request that can be satisfied from the cache. And we have the 3 letters, and X, Z, and W. And the X, NI means that user I is requesting for the file N. And Z, NIG means that there is a route between the user I and the cache G for the file N. And WNIG is basically the weight, so for like each file and for like every request. So if the weight is not 0, and also there is a request from I, and there's also a route from I to the cache G for the file N, then we can say that the request from I is being satisfied, and that is a hit. But there are some constraints, and such as we can say there is a letter Y, which we haven't talked about before, and the letter Y is very relevant to the root Z. And what is Y? The YNG means that whether the file N is stored in the cache J, and that is very relevant to the root, because if there does not have such files, then we cannot rotate. And also the Y is being constrained by the cache capacity. So basically all the files are being stored on J, and there should be a less than or like equal to the size of the cache G. And then we see that how the Y and the L provides an impact on Z. So basically, we say we cannot route I to G if I cannot reach G, and basically we just show that in letter L, or the G does not have the file N, and which we show in the letter Y. Okay, and there is one more constraint that we should satisfy. It's basically that every request from I should be routed. And to solve this, they set up a special node or a special cache G is equal to 0. And that node have all the files and it's being reachable to every user I. So now we have the goal and we have also having these constraints. And then the author need to show how to find the solution. So first they show that the function is concave, and which means that there is an optimal solution to solve it. And then they show how we can calculate a super gradient for this optimization so that we can find such point. And finally, they show that there is an upper bound on the regrets, and which means that the method is always able to have a promising performances. Then the author show their method with the simulation, and we can say in the color blue is the best possible solution, and the color red is their proposed solution. And we can say that their method is quite close to the best possible solution and compared with other baseline methods. So in the paper, they did a comprehensive review of the previous cache methods, and they have also proposed a novel method combined with the idea of online learning. And they have also shown how to use their method to the bipartite graphs. And finally, they've also validated their method on the simulation data. And here's our reference. And thank you very much.